Now C equal to B minus 1 and B equal to two into C. Right now we have another process which is called P2, and inside the P2 we have some code, and this D is equal to 2 into B and B is equal to D minus 1. So let's say this is my code, and these two process has a common variable. You can say B is the common variable in these two processes. Okay. Now this is again a gate question, and what is the question in this? It has been asked like, here B is the shared variable with the initial value of B equal to 2. So B equal to 2 is the initial value for B, and our question is how many different value of B can have? How many different value B can have? Okay, so this is my question, where how many different value B can have. What is the meaning of that is, let's say we have two processes and these two processes are running into the machine, and we need to know that what should be the value for B. Now here we can do many combinations. So in traditional system we use preemption, right? So what happened in the preemption? The process which are running into the CPU may be forcefully removed from the CPU, and another process will be taking its place, and it will execute its instruction. Now here we have different scenarios that can be possible. Like let's say P1 is executing all its instruction and then P2 will execute, or P2 will execute first and then P1 will execute, or P1, some of the code of P1 will execute and then some of the code of P2 will execute, and then some of the code of P1 and then some of the code of P2. So it depends upon different type of scheduling what we can use. So let's say you assume that we have given some numbers to these instructions. Let's say this is 1, this is 2, this is instruction number 3, and this is the instruction number 4. So we have 4 instructions, as you can see, right? Now let's talk about some of the values that can be coming. Let's say we are having one instruction 1 will execute, then 2 will execute, then 3 will execute, and then 4 will execute. It is P1 will execute first and then P2 will execute. Then what is the value of B? So what will be the value of B? The initial value of B is 2. So we'll take C equal to 2 minus 1. So C will become 1. Then what is the value of B right now? It will be 1 into 2. So it will be 2. So right now B value is 2. After that, we are going to execute this code, which says that D equal to 2 into B. So 2 into B, what is the value of B is 2. So D will become 4. And at last, what is the value of B? The value of B will become, it will be 4. 4 minus 1, it will be 3. So this is one value that we have got at very last, right? So this is the B value that we got when we execute these in this particular sequence. Let's say we have another sequence. Let's say we'll execute P2 first and then P1. So once we'll execute P2, so it will execute the instruction 3, then 4, and then 1, and then 2, right? This is the sequence. Now let's go and find out the value of D. So D will be, because the initial value of B is 2, so it will be 2 into 2, it will be 4. Now B, intermediate B value will be 4 minus 1, it is 3. And then we'll go to the instruction 1, we'll find out the value of C. It will be B. What is the value of B? Is 3. 3 minus 1 is 2. And then B will be equal to 2 into 2, it will be 4. So this is another value that we got with this particular sequence. Okay, let's have another sequence. Let's say we are having the instruction 1 executing, and then the P1 will be preempted. Let's say there is a round robin fashion. We are executing for 2 microsecond or 2 millisecond. So one instruction will execute, and then another instruction of another process will execute, then another instruction of the previous process will execute, and then in that way. So let's say the sequence is 1, 3, and then 2 and the 4, right? If this is the sequence 1, 3, 2 and the 4. So what value you will get? So we may get C equal to, so what is the initial value of B is 2? It will be 1. Then we'll find out the value of D is again 2 into 2, it will be 4. Now instruction number 2, it will be giving you the intermediate value of B. It will be 2 into C. What is the value of C is 2. So sorry, C is 1, so it will be 2. And what is the value of B here? By this, it will be 4 minus 1, it will be 3. So here again you will get the value 3, right? Now let's execute in a reverse way. Reverse way means 1, 1, 3, 1, 3, 2 and 4 we have taken, right? Let's take a reverse way. 3, 1 and then 4, 2. 3, 1, 3, 1 and then 4 and 2. Now if we'll execute in this way, then what is the value of D? D will become, initial value of B is 2, it will be 4. What is of the instruction 1, C equal to B is 2, it will be 1. Then 4, instruction 4, which is the intermediate value of B will be 3, and the last value will be 2 into C, it will be 2. So this is another value that we'll get. Can we do other sequence? Yes, we can do other sequences. Let's say we are executing instruction 1, then 3 and 4, and then 2. It is possible, right? Instruction 1 will execute, then it will be preempted. Instruction 3 and 4 will be executing, means all the instruction of P2, and then instruction 2 will come. So this might be the sequence. So 1, 3, 4, and 2. Yes. So if we'll execute 1, it will be C equal to 1. Then 3, it will be D equal to 4. And then 4, it will be B equal to 3. And what is the last value of B? B equal to 2. Right? Can we make a reverse way? So 1 will execute 3, instruction 3, then it will, the P2 will be preempted, and P1 will execute all its process, and then the rest of the process of P2 will be executed. So the sequence will be 3, 1, 2, and then 4. So if we are doing that, so we'll calculate the value of D first. Is of instruction 3, it will be 4. Then we'll execute C, C is 2, sorry, C is 1, C is 1, and then the value of B will become 2, and the last value of D will be D minus 1, which is 3. So you can see here, we have explore 1, 2, 3, 4, 5, 6 different scenarios of these two processes can execute. Now you can see how many different value of B is there. So we have value of 3. This is value of 3. This is value of 3. This is one similar values. Then we have another value which is 2. And then we have another value which is 4. So we have 3 different values of B. So it might be the option like 2 different value, 3 different values, 4 different values, or 5 different values. So the answer will be 3. So we are getting 3 different values of B. Now why we are doing that? We are doing that to understand that what problem is. The problem here is the race condition. What is the meaning of race condition? The meaning of race condition is both the processes are trying to execute its shared values. And when both the processes will try to execute its shared values, so what will happen is the system will having the inconsistency. As you can see, we are getting different values of B, and B is here the shared value or the shared variable, because B is shared among these two processes. So C is the local variable here, and D is the local variable here, but B is the shared variable that has been used between two processes or two program, you can see. So in each and every program, we have a portion which has some shared resources. That portion is called critical section. Okay, about the critical section we have discussed. So we have some individual or some independent codes, or here also we may have some independent codes, but some codes which are in this particular section is shared code, or you can say shared resources. So as we have discussed in the last class, that what do we mean by shared resources? So shared resources may be the variable, maybe the memory which is shared between two processes or two or more processes, or it may be some sort of codes which are shared, or some sort of hardware that could be shared between two processes. It may be your printer, it may be your scanner, or it may be your other hardware devices like network card or something, or switches, or any other routers, let's say. So two processes can have many shared things, right? So in the last class, we have discussed about this critical section. So while we have the shared resources in the program, or you can say when we have the critical section in the program, so this particular critical section should be handled in a very precise way. And this could not be handled in a light way. Means we cannot do a serial process of these two program, right? We cannot do some sort of you can say the intermediate process also. So it depend upon something like, if a process want to go into its critical section, and what is a critical section? Is the part of the code where there is some shared resources. So if a process want to enter in its own critical section, so it has to go through the precondition. So there is another section which is called precondition. After the precondition, the control will go, if the precondition satisfied, then the control will go to the critical section. And once a program is executing the critical section, so no other program will allow to enter into its own critical section. And then once this particular process will execute its critical section and done its execution, then there is the exit condition. Exit condition or exit code, you can say. Okay, some sort of codes. Exit code need to be executed by the program, and then it will do its own local program or local code it can execute afterwards. So what I want to say is, this is very much important, is the precondition of the critical section and the exit code or the exit condition that need to be done by the critical section. Now and we know about the inter-process communication, right? What is inter-process communication? Two processes need to talk to each other or by two things. Either it will have the shared memory, which is like it will be shared between two or more processes. So the address space of one process will be overlapped by another process, and that overlap portion is nothing but the shared memory. And another way of inter-process communication is message passing. So messages will be given to the kernel, and from the kernel another process will take it. So here we are talking about some sort of memory, some sort of variable, some sort of codes. So here one is updating something into the variable, or another is using the updated value. Means there is, in this particular critical section, one process may do write operation and another process may do read operation. Or you can say that may be in a reverse way. So one P2 also can write and P1 also can read, right? So P2 can, if P2 is writing, then P2 can read it, or if P1 is writing, then P2 can read it. So we have seen one example which is called producer consumer problem that we have seen in the last class. So producer need to produce all the time and consumer need to consume all the time. And in this particular example, we have seen the unbounded memory or unbounded space or bounded space or the bounded variable. Not the bounded memory, right? Or the bounded buffer. So we have unbounded buffer and bounded buffer. Buffer is nothing but is some sort of memory which is shared between two processes, or some sort of variable that will be shared between two processes. So that is nothing but a problem which we have understood, and we have find out that one process is updating something, then another process will take the updated value or the read the updated value. Now here what we understood with this particular example, we understood like both the processes are trying to manipulate its or trying to access its critical section. This is the critical section of P1 and this is the critical section of P2. But here we doesn't have any precondition or we doesn't have any post condition. Here also we doesn't have any precondition or we doesn't have any post condition. So if we doesn't have any precondition, so definitely anytime this process can execute its code, or anytime this process also can execute its code, right? So that particular thing is called race condition. So I think you understood what do you mean by race condition. Both the processes trying to execute its critical section without any precondition, and it will lead to the whole system in a inconsistent state. That is called race condition. We know about critical section, we know what do you mean by precondition, and we know what do you mean by exit code or the exit condition. Okay. Now, what is the solution for that? So the solution for that is to write some sort of code or some sort of program or some sort of algorithm which will satisfy at least two essential condition and two non-essential conditions. So generally we have, in some book it says that we have three conditions that will be satisfied, or in some book it is written four conditions that has to be satisfied. Now what are those conditions? So we'll see one by one. So the first condition is mutual exclusion. Second condition is race the progress. Third one is bounded weight. And the fourth one says that there will be the assumption like in the hardware there is there will be no speed. So there will be no speed issue and there will be no hardware issues. So you can say it is related to the hardware. It says that there will be no speed. So speed we will not going to consider for that. The hardware speed is not going to consider for that. Here these two conditions are, you can say, the essential condition that has to be satisfied. These essential condition, and these two conditions are non-essential condition, but yeah, desired condition you can say, where in the program we assume that this condition always take care by the programmer, that it will not consider hardware speed or hardware related assumptions in its algorithm. It will take only these three conditions need to be satisfied. From that, the first and the second condition is essential. Without, if we have these two conditions, we can say that the algorithm is good, very good. If we have bounded weight, then we can say very, very good, right? And this is always been satisfied by that. So let's see one example and try to understand what is the meaning of mutual exclusion, what is the meaning of progress, what is bounded weight, and what is the hardware speed and all. Okay, let's take an example where we have two process P0 and process P1. Process P0 has while loop, and inside that another while loop is there. It will say turn not equal to 0. If turn not equal to 0 means if the condition satisfy, it will go to the you can say bounded wait, or you can say some sort of loop. Okay, self loop. Then we have critical section part. This is my critical section. And then we have turn equal to 1. We will do that, turn equal to 1. And then we have the remainder of the section. Reminder to the section of your program. So this is my P0. Let's see P1. So we have while loop again. Inside that we have while. And here we'll test for the turn variable, which is not equal to 1. Once it will satisfy, it will go to the infinite loop. Then we have the critical section. And then what we do is we'll make turn equal to 0. And we have the remainder section. Okay. So let's say these are your two programs or two processes. Okay. And what we know about the critical section? So we know that if we have any process, so it has to go to the entry section, and then it can go to the critical section. And then after that, we have exit code or exit section. And then we have the remainder section. So remainder section is nothing but your remainder of the program. Now here, this is my critical section. And before that, I have the entry section, and then we have the exit section. Now entry section is some sort of condition that need to be satisfied. If it is satisfying, a process can come into the critical section, execute its code, and then it will exit. Now what is our objective? Our objective is to satisfy mutual exclusion, progress, and bounded wait. Yes, bounded waiting we have. So what is mutual condition, what is progress, and what is bounded wait? And the hardware part, as I told you, it is already understood that it will be satisfied. What is mutual exclusion? Mutual exclusion says that if one process are executing into the critical section, so other process are not at all allowed into the critical section. This is called mutual exclusion. Means if one process satisfy the entry condition and it will be there in the critical section, so no other process will allow into the critical section at that particular time. So this is my mutual exclusion condition. Okay. The second condition is progress. What progress is? The progress is that if nobody or no process are in the critical section, so we should allow the process who are interested to go into the critical section. Understood? If the critical section is free, means no process are into the critical section, so we can allow a interested process or the process who are interested to go into the critical section, and no other process will going to stop it to go into the critical section if critical section is free. Another thing is in the progress is, as I told you, if a process is interested. So here in the progress, we take the call of a process, whether a process want to go into the critical section or whether a process do not want to go to the critical section. So we have to think of the interest of the process, whether process want to go into the critical section or do not want to go to the critical section. So we have to ask the process whether you want to go to the critical section or not. And we have to put only the interested process into the critical section. If a process is not interested and forcefully we are putting into the critical section, that is not progress. Means my algorithm is not satisfying progress. So I think you understood what is the meaning of progress. So the interested process only, if critical section is free, so will allow interested process who want to make an interest to go into the critical section, will allow that particular process to go into the critical section. Okay, that is called progress. Now the last one is called bounded wait. Let's say one process is interested and want to go into the critical section, but other process are not leaving the critical section. So how much time the interested process will wait outside the critical section? So if we are making that particular wait to a bounded wait, means this is your maximum time you can wait. So that maximum, and after that there will be the guarantee that the process will get into the critical section. That is called bounded wait. Means will allow the process, first of all will allow the interested process to go into the critical section, but somehow if some other process are using the critical section, so the interested process has to wait for a bounded period of time, and after that that process will get the chance. So here we guarantee that a process, if a process is interested, it can go and execute its critical section for after some time. So that some time is bounded wait. So let's talk about the solution of it. So right now we are looking for two process solution. Two process solution, and we'll see that how we can extend it or how we can take it further, the two process solution. Okay, so here P1 and P2 are the two processes. As you can see, these two processes are having some sort of code. Here you can say this is a while loop and it is always one, means these piece of code has to be run all the time. And here also it says that these piece of code has to be run all the time. Here we have the critical section. The meaning of critical section is here in this section, both the process are sharing some resources. Process 1 as well as process 2 are sharing some resources. Let's say the turn value, the initial value of turn, so we can take 0 or we can take 1. Anything we can take as a turn value. So let's assume that we are taking turn as 0. Okay, and we'll go for P0 first. Let's go to the P0 first to taking turn as 0. Now if we'll take turn as 0, and you can see the turn is also shared between these two, and we have the critical section also. Now let's go to the P0. We are executing P0. Once we'll execute the P0, because it is a while loop and this is 1, so we'll go to the definition of while loop. Here the first line is while turn not equal to 0. But what is turn? Turn is equal to 0, right? So that condition is satisfied or not satisfied? This condition is not at all satisfied. because 0 does not equal to 0. 0 should be equal to 0. So if turn value is 0, 0 is not equal to 0, that is not satisfy. If it is not satisfy, so we'll go out of that particular loop. So once we'll go out of the loop, we'll go to the critical section. Now P0 is in the critical section and executing its critical section, and then after that P2 will be exiting from the critical section. So it is an exit section and this is the entry section. You can see this is the entry section and this is the exit section. So P0 will be executing its critical section, and once it will out, the turn value will be 1. Now can we say that P0 can again go to the critical section? So let's see that. P0, it is in the while loop, it will go inside it while turn not equal to 1. Turn not equal to 1. So we have the value of 1. Turn not equal to 0. It means that 1 not equal to 0. Yes, the condition is satisfied. So it will go to the loop. Loop means it will not go to the critical section. So it is like that. So we have this entry section. Inside the entry section, we have a condition that need to be satisfied. If it is satisfied, it will be in a loop. If it is not satisfied, it will execute the critical section. Getting it? If it is not satisfied, it will be executing the critical section. If the condition is satisfied, it will be in a loop. So what we are doing is we are preventing P0 to go into the critical section. Getting it? Now let's talk about at that particular time, can P1 can go to the critical section? So let's see, P1 is interested to go into the critical section. So it will go to this particular entry section and it will execute the entry section, turn not equal to 1. So it says that 1 not equal to 1. It is wrong. 1 is equal to 1. So this condition does not satisfy. If it is not satisfied, where it will go? It will go to the critical section. It will execute the critical section and make turn equal to 0. So once it will make turn equal to 0, now P0 is in the loop. It is testing all the time whether the turn value is not equal to 0, whether the turn value is not equal to 0. If turn equal to 0, then this condition not at all satisfied. Then it will go again out into the critical section and P0 will execute its critical section. And then again it will make it turn equal to 1. Right? It will do like that. Let's assume that P0 is in the critical section. It is not out from the critical section, right? And we'll look for the mutual exclusion, whether this code satisfies the mutual exclusion or not. What is the meaning of mutual exclusion? The meaning of mutual exclusion is if a program is in the critical section, can another program will go into their critical section? So if we restrict other program to go into the critical section, if another process are using its critical section, so that is called mutual exclusion and we satisfy the mutual exclusion. Now let's assume that if turn equal to 0 and this condition is not satisfied, then it will go to the critical section. So P0 is in the critical section. At that same time, can we preempt P0? Yes, we can prevent. So prevention can be done at any time. So right now P0 is in the critical section and executing its critical section code, and we have preempted it. And right now P1 want to go into the critical section. Now if P1 want to go into the critical section, then it has to go to the entry section and execute the entry section. Anti-section says that turn not equal to 1. So what is the turn value? Turn value is 0. 0 is not equal to 1. Satisfied? So if it is satisfied, it will go into the loop only. It will not allow into the critical section. So you can see that mutual exclusion, it will preserve. The mutual exclusion is there in this particular code, right? So if one process are in the critical section, this P0 is not at all allowed into the critical section, because we have a condition, and that condition will make sure that no other process will get into the critical section if one process is already there in the critical section. So this particular code, yes, it satisfies mutual exclusion. Getting it? Now let's see another scenario where we can see that whether this particular code is satisfying the progress or not. So what is progress? The progress is, if a process is interested to go into the critical section and no other process are in the critical section, do we have to allow or not? Okay. So let's talk about the same scenario. We'll start with turn equal to 0, and we'll see P0 is executing. 0 does not equal to 0. 0 is not equal to 0, which is wrong. If it is wrong, it will go to the critical section, execute it critical section, and it will make it turn equal to 1. Now nobody is in the critical section. Now again, P0 want to go to the critical section. Again, P0, because nobody is in the critical section, right? So P0 executed its critical section, out of the critical section, now it is in the exit section. And P is thinking that I again want to go to the critical section. Can we allow this particular program? So turn is 1 right now. So 1 is not equal to 0, yes. Then we are in the loop, and till the turn is equal to 1, the P0 will be in the loop. Means the P0 is not allowed to go into the critical section, even critical section is free. So can we say that progress is preserved here, or progress is there in the algorithm or in this particular solution? No, progress is not there in the solution. Means if a process is interested, you are not allowing the process to be executed into the critical section if critical section is free. Now another scenario is, if P1 is interested, it can go into the critical section by turn equal to 1. So 1 is not equal to 1, not satisfied, it will go to the critical section. Let's say P1 is not interested. So this particular code is having the strict alteration. Means if P1 is executing once, then P2 has to execute once. Then only it will make turn equal to 0, and then P0 will allow, and then it will make turn equal to 1, and then P1 is allowed. So what is there? It is a strict alternation. Means if one process is not interested, but you are saying, your code is saying that you have to execute the critical section. All right. So without the interest of any process, you are forcefully saying that you have to execute the critical section, because other process are waiting in the loop, and that process is interested, and we are not allowing the process to go into the critical section. So both the condition of progress is not at all fulfilled here. So progress is not at all fulfilled. Now what about these are the two essential conditions. So two essential conditions has to satisfy, because one is satisfied, one is not satisfied. So we can say that overall this algorithm or this piece of code are not for the mutual exclusion solution. This is not for the mutual exclusion solution. Now let's go to the bounded weight. Is this satisfy bounded weight? Because it is not satisfying progress, it is not at all satisfying the bounded weight also. Because let's assume that after P0 will execute itself, execute itself, P0 again want to go to the critical section. But here, no matter how much P0 has to wait, without executing P1, we cannot allow P0 to execute. So P0 has to wait for infinite times, right? Infinite time in this particular code, if P1 is not interested to go into the critical section. So I think it is clear that bounded waiting is also not satisfied here. Bounded waiting says that the waiting should be bounded for a certain period of time. If somebody is interested and nobody is in the loop, or if somebody is interested and it is waiting for there and it is interested to go into the critical section, so your code should allow that particular process which are interested to go into the critical section for a certain period of time. That period should be bounded. It is not unbounded waiting, means it is not infinite waiting. But here in this code, there is infinite waiting is happening. Okay.